Welcome back to our online class. Today we'll be discussing the Faraday's law of electromagnetic induction, and we'll be also considering its relationship, with self-induced EMF, mutually induced EMF, and all that. So we're going to derive some formulas. First, to start with the first law of Faraday's of electromagnetic induction. Here we have, it says that whenever a conductor cuts across the magnetic field, an EMF, an electromotive force is induced in the conductor. That is, take for instance, we set up a magnetic field. That is, we have permanent magnets. Let's say permanent magnet. Now let's say this is the north pole, this is the south pole. What happens? There will be a field, magnetic field, in that region. Now, if I should bring a current carrying conductor, let's say a conductor here, we are made to know that this conductor will cause an EMF to be induced. That an EMF will be induced in the conductor. You get now? Because this there will be a relationship that will cause a force here. A force will push this down in the downward direction from here, and a force here again going upward. So there's going to be an EMF induced in the conductor. That's the first law. Now the second law, we have that the magnitude of induced EMF in a coil is directly proportional to the rate of change of flux linkages. Now we'll be concerned majorly with this second law. Let us write it mathematically. The second law mathematically said the magnitude of induced EMF, let our induced EMF be E, is directly proportional to the rate of change of flux. Now, what is rate of change of flux? Rate of change of flux is phi 2, let's say phi 2 minus phi 1 over T. Do you get it now? That is, as the flux changes with time. So, here we have this into this minus, this over T. So this is our rate of change of flux. Rate of change of flux. Now, very good. If I bring in a constant here of proportionality, I'm going to have E to be directly proportional to, let's say, N into phi 2 minus phi 1 over T, right? Now, if I bring in the differential form of this, I'm going to have E to be equal to N the phi over the T. Now, this is going to be negative according to Lenz's law, because Lenz made us understand that the Lenz's law of electromagnetic induction made us understand that the EMF induced tends to produce a current which opposes the motion of the flux that produce the induced EMF. So it means it's in the negative direction. So this induced EMF produce, a current. The direction of the induced EMF, produce the current which is in opposition to the rate of change of flux that produced it. So that is why this is going to be what? Negative. Now, recall again that if you have to follow the second law, E, we know that E is equal to phi over what? The T. Now let us call this one equation 1. You know that phi, again, is equal to what? The flux density multiplied by the area. Here we are going to consider the area of the conductor, the area served by the conductor. Now, and again, okay, let's put the T. And our area is the length multiplied by the small distance. That is B multiplied by length multiplied by the X. That's the small distance over the T. You know that the X over the T is velocity. So our E is equal to what? B multiplied by L, and the x over dt is going to give us V. Now, if it's at an angle, you know that E will be equal to B multiplied by the length, where your B is the flux density, multiplied by V multiplied by the sine of the angle. So let us call this one equation 2 and this one equation 3. Now, we're going to consider a self-induced EMF. Now, self-induced EMF. Now, for a self-induced EMF is an EMF induced due to the change of flux produced by it linking with its own turns. That is, the coil itself, is the EMF induced here is due to what? The change of flux produced by it linking with its own turns. Now, and recall again that this is dependent on the rate of change of current. That is, the EMF induced is dependent on this rate of change of flux, and the rate of change of flux also is dependent on the rate of change of current. Then it shows that our E is what? Directly proportional to the I over what? dt. Now, if I bring a constant of proportionality, I will have E to be equal to, let's say, L di dt. Now, this is the equation for a self-induced EMF. Let's call that equation 4. Now, recall that I told you that the EMF induced is proportional to the rate of change of flux, and now it is directly proportional again to the rate of change of current. It means I can equate this and this. Then we say E is equal to N, let's say the phi over dt, and is equal to L di dt. Now, let me take an integrated value of it so that I will have a whole of it, so that I will have N phi to be equal to Li. Now, my L here, by making else of the formula, will be equal to what? N phi over what? I. Now, this is equation what? 5. So, you can see any of these in the question. That is what we want to come and do today. We are doing to this class. So, we have N phi over I. So, it means that the L, that is the constant of proportionality for induced EMF, is N phi over I. Now, let us now go to mutually induced EMF. For mutually induced EMF, this is the EMF induced due to the change, of flux produced by another coil, not the same coil. In self-induced EMF, we said it is an EMF produced due to what? The change of flux in that coil. But in mutually induced EMF, the EMF here is induced due to change of flux produced by another coil. Then it means that the EMF in a coil, say E, will be directly proportional to what? The rate of change of current. Let's say another one. If this is B, then it will be directly proportional to that A over T. Let's say let's call this one A, or I. Let's call it A. EMF induced in B is directly proportional to what? The rate of change of current in A. That is, what we have here will give me the EMF induced here. Are we together? If I bring in a constant of proportionality, then my EB will be equal to, let's say, M constant dia over what? dt. So, generally, since the EMF will be the same, I can say E equals M dia over what? dt. Now, recall again that, or know that energy stored in an inductor. Energy, so let's call this one equation 6. Energy stored in an inductor is given as W equals to 1 over 2 Li squared. And let us call that one equation 7. So try to remember that we derived all this from the second law. Then we have the self-induced EMF. We're able to generate our L, inductor as constant of proportionality for self-induced EMF. This is the relationship where your N, number of turns here, multiply the flux over the current, and down to the mutually induced EMF, and the energy stored in an inductor is given by W equals to half Li squared, all in joules. So remember, the deal is that you must be happy, I must be happy, we must be happy. So endeavor to subscribe, like, comment, and share. Thank you.